Hello, and welcome to Chapter 8, Section 3. Today we're talking about a one-sample t interval or a one-sample z interval for a population mean. So we're still doing confidence intervals here. It's just two new names for it. So if you remember our process from last time, we're panicking. So when we name the interval, these are the two names that we'll add on to our list today. So just as a quick reminder, our confidence interval formula is where you have the statistic plus or minus the critical value times the standard deviation of the statistic. So here, because we're going to be trying to estimate a population mean using a confidence interval, then our statistic's going to be the sample mean. So in symbols, it would look like this. We have x bar, because remember x bar, we use that to stand for our sample mean. And then we're adding and subtracting our critical value of z star times our standard deviation of the statistic, which from last chapter, we have sigma, the standard deviation of the population, divided by the square root of your sample size, n. Okay, so one thing about this formula is that this actually isn't used a whole lot, because this part right here, the standard deviation of the population, how would you know that? Because if we're trying to estimate a population mean, we don't know the population mean. But if you think back to the formula for calculating a population standard deviation or standard deviation in general, you would need to know what the mean is in order to calculate that distance away from the mean. So this is why this formula is not very feasible. It's not very realistic. So a lot of times what you'll see instead for the standard deviation of the population, they'll kind of base the standard deviation on past studies. So it's not truly a population standard deviation. It's kind of like from past experience, from past studies, we figured out that the standard deviation is going to be whatever number. So a more realistic confidence interval formula would be like this, where we have the sample mean, so x bar plus or minus, and then I'm going to introduce you to a new critical value. We'll call it t star. And then for the standard deviation of the statistic, it'll be the standard deviation of the sample. So that's what we have, like this s sub x is. Sometimes you'll just see it as s, but really it's the standard deviation of the sample divided by the square root of n, so our sample size. So let's talk about the t star a little bit. It comes from the t distribution, so it's kind of like a normal curve, but slightly different shaped. So when I mean slightly different shaped, it's more squashed down. So like if you took the normal curve, and I have a picture here, so here's like our regular normal curve here, this taller one. And if you kind of like squished it down horizontally, then that becomes the t distribution. So with this t distribution, it's still a density curve, so the area under it is still 1, but if you can kind of see, the ends are more spread out and a little bit taller to accommodate that area. The craziest thing about the t distribution is this shape actually changes. So depending on the sample size, the shape will change. As n, your sample size increases, so like larger sample sizes, that means the t distribution, it actually gets kind of taller and like unsquashed, and so it gets closer to that normal curve shape. And so this is why we want large sample sizes. So that means this shape that you see right here, this is when n is actually a small sample size. So so that's why we don't want small sample sizes, but also that central limit theorem even more so applies here. Because when we're dealing with larger sample sizes, the shape of the distribution will be closer to approximately normal, and that's why we need to use that here. The last thing is this thing called degrees of freedom. So we abbreviate it with df, and this is something that you'll need to use in order to use the table for our t distribution, because it's not the same table as our normal curve. So table A is not the only table we have anymore. So degrees of freedom is basically when we have a set of data and we're doing calculations on the set of data, either calculating standard deviation, the mean, anything of that sort, when we're doing calculations on it, the degrees of freedom is basically the number of variables that have the freedom to be independent. And it's kind of a weird concept. So let's say we're doing a calculation for the standard deviation. Then let's say we have also 10 data points in our sample. So when we calculate that standard deviation, whatever the standard deviation number is, there's 9 values in our data set that can really be any number that they want. So I know it's kind of weird, but because numbers don't have feelings, but they are free to be whatever number that they want to be. But then there's that one value, that last one. In order to make the calculation equal whatever the standard deviation is, that last value has to be a certain number in order to make the calculation equal. So because there's that one last value that doesn't get to choose whatever number it wants to be, that's why we have degrees of freedom being n minus 1, so your sample size minus 1, because most of the values in your data set are able to be whatever they want except for that last one, and so that's why we have this degrees of freedom. So in the table, I've included it. This is part of the AP Statistics formula sheet. It's the table, they call it Table B. It's right after your normal curve one. And so the top picture looks similar, except you'll see the T star here instead. So the table is also read slightly different. Instead of z-scores going down the side, there's DF, so the degrees of freedom. So that's how you start by looking it up. So whatever your sample size is, subtract it from 1, and that'll tell you which row to look at. Another difference with this table is that it tells you the tail probability going across this top. So totally different than z-scores and the first decimal, second decimal going across the top. So tail probability basically means what area is at each of the tails. So here, this first row where it says 0.25 as the tail probability, that means this shaded area is 0.25, so 25%. But it also means that on the other side, there's also 0.25 on that side as well. This is especially useful for when we're trying to calculate confidence intervals, because when we're calculating our critical values, we're basically looking at what percent is in the middle so that we can figure out what percent's on the sides. So let's say we're trying to do a 90% confidence interval. That means 90% has to be in the middle, and then 10% on both sides, so that means it's 5% on each side. So 5% on each side means the decimal place would be 0.05. So we would be looking at this column right here, where at the top the tail probability is 0.05. And then whatever your degrees of freedom is, you would crisscross that to figure out what T star to use. So let's do an example. Let's say I'm trying to find a 90% confidence interval where our sample size is 30. So that means for a 90% confidence interval, we'd have 5% to the left and to the right of that curve. And so we're looking at the tail probability of 0.05. N equals 30 means my degrees of freedom is going to be 29, because 30 minus 1. Really good at subtraction. So I'm going to use my n equals 29 row here and end up with T star equals 1.699. Okay, not too crazy. Let's do another example just for fun. This time let's try to do an 99% confidence interval. Let's say this time n was 50. So we have large sample sizes. This is great. Okay, so with a 99% confidence interval, that means the tail area is going to be 1% combined, which means 0.5% on each side. So 0.5% is 0.005. So that means we're looking at this column here. N equals 50 means my degrees of freedom is 49. So 49, if you look down my degrees of freedom, there is no 49. Super awkward. So 50 would be the closest. However, if we say 50 is our degrees of freedom, we should actually have a sample size of 51. But we can't lie about our sample size being bigger than it actually is. Because you know how we've been saying the bigger your sample size, the better it is. Well, you can't just claim that you have better sample sizes when you don't actually. So what we have to do is actually go down to the next closest one. So you can't round up with degrees of freedom. You always have to round down. So if my degrees of freedom was 49, the next closest one would be 40. And so my T star would end up being right here, 2.704. Okay, so this table then obviously is not going to be the most accurate, just because like whenever we have to round down like that with our degrees of freedom, it gets a little awkward. We're going to be not quite as accurate as we want. So that's why we have a graphing calculator. So a graphing calculator will be much more accurate because it doesn't skip degrees of freedom like this. So using my graphing calculator, let's say I'm trying to find the T star, the critical value for a 90% confidence interval where n equals 30. So to do that, you're going to go second vars. This is the menu where you usually go to find your normal CDF. Underneath it, you have the inverse norm. Underneath that, you have inverse T. So inverse T is basically like inverse norm, but for T distributions. So we're trying to find that T star, and that's why we're going to use inverse T. If you have an older calculator, like a TI-83 or older, I don't think you have this function, so you are stuck relying on the table, just so you're aware. So if you have a TI-84, you should, or newer, you should be able to see this inverse T function. So choose number 4. It'll ask you for the area. So that area is just that tail probability that we were talking about. So for a 90% confidence interval, the tail probability is 0.05. Degrees of freedom, you're just going to type in 29 because our n was 30 here. Paste, enter one more time. And it'll give you the negative version, but remember our critical values are always going to be positive because we like positive numbers. So negative 1.699, pretty much what we had. And if we do it for the one where we had to round down for our degrees of freedom, it should be more accurate. So second vars, number 4. This time our area was 0.005 for our tail area, and our degrees of freedom was 49 in this case. So in the calculator, you don't have to round down. Just type it in exactly what your degrees of freedom is, and then we end up with negative 2.6799. And so this one is actually more accurate, and again, we always take the positive version of it rather than our 2.704 from the table. All right, so now you have both ways of finding your critical value for a T distribution. One other thing I want to point out about this table that I think is very helpful is if you look down at the very bottom where the degrees of freedom says infinity, like what the heck, infinity? So degrees of freedom, when it equals infinity, it's just basically saying this is the normal curve, because the normal curve is like the perfect one where your sample size is the largest possible. And so what I like about it is that at the bottom row, it also already lists out your confidence level. So earlier when we said 90% confidence, if you looked at the tail probability of 0.05, if you go all the way down, it already tells you the confidence level is 90. So really, if they're asking you for a 90% confidence interval, you can just go backwards and not have to calculate the tail probability. So 90% here, look for your degrees of freedom. That also means if your degrees of freedom is infinity, it already gives you the Z star. That's what I love about this table. 90% confidence interval, the Z star is 1.645. And that's a number that you should have recognized by now because we use it so much. And like a 95% confidence interval is 1.960 for a critical value, and so on. So that's all listed out there for you. It just makes your life a little bit easier because you don't have to calculate it yourself. But yeah, that's another pro to this table. Okay, so one other thing that I want to talk about for this section then. As we're calculating confidence intervals, we know we have to use that panic process. So most of it is the same. It's just, when we do panic. So the changes that really occur when we do our panic process is that the parameter, you just need to make sure that you're stating you are trying to estimate the population mean, because last section we talked about a population proportion. Okay, make sure you include the context. In your assumptions or conditions, you still need the random independent samples. that we talked about last time, you also need a normal shape. So for this type of problem, when we're dealing with means instead of proportions, in order to check this, it's not the large counts rule. We either need to make sure that the original problem is stated as normal. So if that's the case, you just say that it's given. If you don't have that, then you need to make sure that you have a large sample size. And so we would cite the CLT for that. So our sample size is large, so the central limit theorem says our distribution is approximately normal. If you don't have a large sample size, that means that this problem you can't actually do. Your confidence interval would not be accurate, would not really make sense, so you really can't. That doesn't occur a whole lot because on a test, when would anybody give you a question where like, I can't do this, and then you move on with your life? So that doesn't really make sense, but just so you're aware, like if they ever say like, what is the problem with this? Or is there any mistake with this problem? That's what's something you should be looking for. The name of the test or of the confidence interval will be either, from our title, the one sample Z interval for a population mean or a one sample T interval for a population mean. The interval itself, we have the formula from above. Either one of these. So remember, this is where you have to differentiate like which kind of standard deviation are you given? Is it from a population or a previous study, or is it a standard deviation from a sample? So that's how you determine whether it's going to be the Z interval or the T interval. And then lastly, the conclusion, same wording as before, plug in your context, say mean instead of proportion. That's the differences. And the last thing I want to talk about in this section is being able to calculate a sample size given a margin of error. So this is kind of like our solve for n problems from last section. We just have a different formula for our margin of error because our standard deviation of the statistic is different here. So remember, it's like the Z star times whatever your standard deviation is, and that's what you're setting your the margin of error equal to. The only thing is, so in this section, we technically also have a T star in here, but they wouldn't ask you to solve for n if you had to figure out the T star also. That would be impossible, because if you don't know your sample size, you can't use the table to calculate your degrees of freedom to find a T star. So for these problems, they're only ever going to give you a population standard deviation so that you can use a Z star in order to calculate your margin of error and then solve for n. So then just basic algebra after that. All right, that's it for this section. Thanks for watching. Don't forget to like and subscribe. Bye.